My name is Martin Roetteler. I lead the applications team at IonQ. My team essentially works very closely with customers. We work hand in hand with them on use cases, exploring them, talking to the developers behind the use cases. We heard in the panel quite a bit about data and the complexity of use cases. Our team essentially talks to the customers directly, tries to also debunk things that likely will lead nowhere, right? Those false leads are also there. But also we then explore real promising directions on like how you might get value out of quantum computing, and in particular today, right? Quantum definitely is today. You heard about our machines. Our machines only get more and more powerful with the upcoming generations of hardware we have. So our mission is literally to show our customers how incredibly valuable it is to own and to access our machines. Okay, so I'm going to unpack a few use cases for you. We have 3 use cases in this presentations we want to double click on. The first one is with a company that many of you are familiar with, Synopsys. It's an electronic design automation and computer-aided engineering company. And they specialize in like helping the semiconductor industry develop chips, but also in digital twins, right? So if you have a large object that you want to simulate on a classical HPC environment, a very typical task is like to study, for instance, vibrations of the object, deformations, crashes of the object. So Synopsys has multiple products, real-world products. They exist. The automotive industry uses them extensively. The aerospace industry uses them extensively. I don't think you can see it very well here. If you want to look there, you see an artist rendering of a finite element of a jet engine. So in a project that we did with Synopsys over the past year, we looked at one of their flagship products. It's called LS Steiner. It's a real-world finite element solver. Looked at models like a Rolls-Royce jet engine. So those are real-world large objects. Okay, so the jet engine, for instance, has about 35 million mesh points and close to 1 billion edges that connect these mesh points. So those are like real-world actual instances. And we worked with Synopsys on a workflow that they already have. Okay, so the input of the workflow is a model like this. The output is you want to understand structural stability, vibrations, and so on of the object. And it's a known problem in the industry that when you get to that certain scale and you run it on a distributed environment, right? This has to be done with distributed computing because it's too large to fit on any kind of single chip, right? So you need some MPI environment to distribute the workload. When you get to that scale, one of the key bottlenecks is the distribution, right? If you do that in a non-smart way, because of the solution of the problem, you might end up with too much communication between the processors. Okay, so it's a known problem that to optimize the communication, you have to spend some time in finding the right solutions. Okay? ANSYS knows that, Synopsys now knows it, everybody knows this. So our team specializes in various technology. We develop, for instance, for the healthcare life science community, we develop specialized solutions. We will see one in a moment. For the optimization field, we also develop specific tools and techniques that can be used as improving solvers. So with Synopsys, we put one of our solvers into that workflow, in the finite element workflow. In one of the stages, you solve an optimization problem. That's exactly where we inserted our quantum solution. And then we were able to measure end-to-end what happens when you do that. Okay, so that's something worth repeating. This is an actual workflow. We're able to measure end-to-end the performance of this workflow. Instrumentation, this runs in the cloud. This is an actual installation of that workflow. And we insert a quantum computer into the workflow and now measure what happens. Okay, and we find that we get reductions in the finite, when you finally solve the system of equations on a classical HPC environment, through the optimization we provide, we get consistent improvements of around 7% and peak performance about 15% reduction. And that is like everything else is equal. Okay, so you basically run this workflow, you have the quantum computer in the loop, and now you get this reduction. You can do 15% more work, you save 15% in cost. So we're extremely excited about this. We're of course curious, is that just a phenomenon, like a one-off phenomenon, or is it more consistent? So we are obsessing about understanding that consistency. And we now looked at a broader range of models from cars, drills, impellers, right? And all of them real-world models. The The drill is that rendering here. It's not a Bosch drill. It's an actual drill that drills down an oil well. That's the drill we looked at. But just they're real world objects, very large, and we can't wait to kind of deliver that impact to the relevant industries like the car industry and so on. So consistent advantages, and as we scale up, right? So right now we are Forte Enterprise, our current generation. We're rolling out Tempo this year. We're already simulating up to 100 qubits using advanced simulators to see what will happen, right? What is that? How is that trajectory of the trend of improvements going to look like? And we see the trend, like in a simulator-based trend, continues to go better, right? You get more qubits, you get better. With Tempo, we expect to be able to prove this out. With the larger systems, we can do even much more. And then once we go to fault tolerance, the sky is the limit, right? We'll have much lower noise rates, not much lower error rates, and we get many more qubits to work with. So this is just primed to be plugged into these workflows. The next example is staying with optimization. So we heard from Roosby in the panel. It's very nice to meet you in person, Roosby. That we're working with Enride, a Swedish transportation company. So Enride makes autonomous trucks, EV powered, but they also work with fleets that are hybrid between fossil-based vehicles and electrically powered vehicles. So it's essentially a transportation as a service company. So we've been working with them for about 6 months to explore use cases. And what's really exciting about that is we get exposed to the real world nature of the workflows. We also get exposed to the developers behind the technology at Enride. And they're experts, the deep experts in optimization, which is amazing because then you actually learn about the real problem and you learn about the real interesting use cases and also pain points. So known pain point in the industry is that when you have your schedule of deliveries for the next week, say, right, you will always get some cancellations. It's just the nature of that business. You get the cancellations that drop in sometimes at the last minute, right? So you want to, of course, optimize your potential of your fleet, right? You want to fill these gaps if you can. And it's an optimization problem. You have typically a choice how you would fill the gaps. And it's kind of a complex optimization problem. It's not really a single objective, right? You might try to fill in as many shipments, but then another thing goes bad, right? You might have to drive too many miles, or maybe you have to switch too many drivers. It's a really gnarly multi-objective optimization problem. So we tackled that. We formulated the problem using a quadratic program, essentially, to capture correlations, spatial correlations between the shipments, time correlations between the shipments, and other things. And we applied our technique again. So one common theme that we often apply is we use decomposition methods to handle a very large scale. Okay, so we are not interested in toy-sized problems. We really want to tackle, like in the case of Synopsys with the jet engine, we want to tackle the cases of like having hundreds of thousands, millions of inputs, right? The dimension should be very large. So again, we applied dimension reduction techniques to break down a very large schedule into kind of a small sub-problem and then tackle that. We're able to plug it back into the Saga platform, which is Enride's one of Enride's key products, and we're able to measure end-to-end what happens when we do that. It looks like a humble 1.5% improvements, but it is an actual improvement. So we can measure this, and of course this is happening on our current generation system. Just imagine what will happen once we scale up the system. So we're super excited about this. We're super excited about the multi-objective nature of the problem, which gives us, again, much to work with. Excited about this partnership. And the third example is from a different domain. We heard from Michael May in the panel, right, that the healthcare and life science industry is full of interesting problems, many of which are extremely hard. And it's also a living business, essentially, right? Like to validate, oftentimes you have to go into the cell or you have to go to a wet lab and validate things. We are extremely fortunate to have AstraZeneca as one of our key customers, and they know a thing or two about healthcare and life science. So we've been working with them for almost 2 years now. And one of the first problems we tackled with them is to understand catalysis-based workflows. So catalysts are extremely important for, of course, the chemical manufacturing industry, like biotech industries. And they're used for multiple things. In this specific example, they're used for the synthesis of drugs. Okay, this is not a drug discovery per se. It's like you know already what you want to target, but now you want to ramp up production, say from a pound or a kilogram to like tons, right? The way to do that is using catalysts. And so in this example, it's probably too small to see up there, but there's a reaction. It's a known reaction based on a catalyst that has a nickel core. Okay, it's a complex molecule, but it has some metals and transition metals in them. And it's known in chemistry that once you get to these kind of metals and transition metals, you need higher order orbitals. If you remember your high school chemistry, right? Higher order orbitals means they're harder to model. And once you have several of these metals in your system, it gets incredibly difficult to do on a classical machine. Even the largest supercomputers struggle with modeling chemistry at that scale. So what we did with them is to take such a reaction and to model the intermediate steps of that reaction and to basically solve the problems that a chemist would solve, right? A computational chemist, the questions they would ask, we solved that for them using a quantum computer. Okay, and the workflow has several stages. It has sort of a CPU stage, a QPU stage, and a GPU stage. Okay, so everything works in tandem in this workflow. The CPU stage is quite simple. It's basically to come up with a model, that's what's the right model of that chemical structure. Then we take snapshots using the quantum computer. It takes snapshots of this quantum state that nature comes up with, right? The electrons, they form like a wave function. We take snapshots with the quantum computer. That takes about a day or two, okay? And then again, it takes a day or two to post-process the data on a classical HPC node. We use AWS for that. It's a pretty beefy node on the cloud. It's called a P5 node for the experts in the audience. And that ran for about, again, 2 days on that beefy node, right? There are multiple H200s in that node, a couple hundreds actually, like 200 plus nodes on that. And what's really cool about the workflow is we got the correct energies out of it. It's already at a scale that people care about. It's not a toy problem. When you look at the quantum computing literature, it's full of like trivial, very small systems. This is not. This has like 130 orbitals, which is very big for chemistry. And we get that, again, through a hybrid workflow that uses quantum and classical. And so now we already showed an improvement in time to solution of almost 600 or 700x, which is already great. But wait, there's more. Actually, we worked on this super hard because we are obsessing about it. Running this for 2 days on a beefy node is not good enough. Okay, so this costs about 400,000 in like real dollars if you did that, right? If you have an on-prem system, you run it on your on-prem system, you're fine. $400,000 is not good enough, okay? So the team is obsessing about improving this workflow. So the team obsessed about this workflow, and in particular the quantum stage and that classical GPU-based post-processing, right, where we already have 650x. So we found another 10x improvement by basically combining different techniques that each one gives us a 2x here, 1.5x here, making those GPU-based codes faster, talking to HPC experts, but also doing quite a bit of like coding with advanced AI models like Opus and Codex. Those help us develop better like solutions for these like optimization problems. And what you see then here is that we made a little dashboard, also vibe-coded dashboard. It's a very fast turnaround if we do that. You see that you can select in this workflow the number of orbitals, that's kind of the chemists care about that, the number of electrons and other parameters. You can also select the kind of SKUs you use on the cloud, right? So in the cloud you have a lot of choices. You can first of all use different hyperscalers. IonQ works with all the hyperscalers, we're on all the clouds. And then you pick your SKU, or you can use an A100, A100, H100, H200, and that impacts cost, right? So for instance, if you, instead of like an A100, which a couple of years ago used to be state of the art, want to use an H100, which is much more expensive, but also much more powerful, then using this workflow, you see that the time to solution goes down, but also your cost will increase. But this is for the example I mentioned before. So instead of 400,000, you're looking at 50,000 or so to discover that workflow, to really get the energies out. And that can have an insane value for a healthcare and life science customer, because now they can actually use this workflow to discover new catalysts. They can discover catalysts with higher yields. Oftentimes regulators impose restrictions on what you're allowed to use in products, right? Like for instance, if you use like some metals that are not environmentally friendly, you might all of a sudden have a problem, and to de-risk that, maybe you want to discover new catalysts. So this workflow is really primed to discover this. We did quite a bit of benchmarking internally on like improving that workflow. And as I mentioned, this is all, like a lot of this work we're using routinely AI these days for on the development side. And it's a good segue to the next presentation, which is given by my team member, Masako Yamada. She leads the AI effort, like the quantum and AI effort at IonQ. And we explored quite a few use cases for that field as well. So as she's coming up, let's give her a round of applause.